Hi everyone. Thank you for tuning in for our talk about solving MongoDB performance riddles with systems thinking. My name is Ger. I am an Area VP for Technical Services Engineering at MongoDB. I'm based in Dublin, Ireland.
Hello, my name is Tom. I am a Senior Technical Service Engineer at MongoDB based in Sydney, Australia.
Tom and I have been involved in solving many real-world performance riddles over the years for MongoDB customers. First, we'll talk about systems thinking in general. Then we'll look at software systems. We'll start with the big picture. We often find the cause of performance problems in application code, frameworks, or underlying technologies like the operating system, virtual machine, or hardware. Next, we'll delve deeper into MongoDB components and subsystems. Later, Tom will walk you step by step through 2 case stories where he'll solve a number of riddles. Finally, we'll provide you with a checklist and pointers to some resources you can use to find the answers to your own performance riddles. So what is systems thinking anyway? A system is a set of elements or components that are organized together and fulfill a purpose. Let's take a look at some real-world examples. First, we have the solar system, our home in the universe. I couldn't find a stock photo on the internet, so here's a model of the system instead. On our planet, we have weather and climate systems. We have institutional systems like a university which contains faculties, professors, and students. We have forests, trees, and animals in the forest. The elephant contains many subsystems which in turn are made up of cells. All of these systems are made up of interconnected elements coherently organized for a purpose. So, systems thinking is about seeing the structures that underlie complex situations. It's all about understanding how to change systems and seeing the deeper patterns lying beneath the events. I highly recommend this book by Donella Meadows, and I'll provide some more references later in this talk. So let's take a closer look at a system which, unfortunately, we've become more familiar with in recent months. This is the model of the spread of a pandemic. In this system, we have inputs, stocks, variables, and feedback loops. The inputs in this case are the fundamental infectivity of the disease and the total population of a city or country. We have 2 stocks, the population who are susceptible to COVID-19 and those who are infected. And we have a variable, the contact frequency, that is the frequency of contacts between people who are infected and uninfected. And COVID-19 ultimately was made worse because of delays between contact, infecting others, and symptoms. And here we see other systems interacting with this system. On the left-hand side, we have social media and media in general, which can influence the contact frequency within a population. And on the right, we see a hospital system, and they're treating a percentage of those infected. Here we see a simpler system, in this case inventory in a store. We have a single stock, that is toilet paper. We have sales on the right-hand side and customer demand, which increases. We have a store manager who perceives the sales, but she perceives that with some delay, and she decides her response and she makes orders. She sends the orders to the factory, and then a number of days later, the factory delivers the toilet paper to the store. So first, let's look at the behavior of this system with no delays. So the store manager, she's trying to keep 10 days of demand in inventory. The demand is consistent, and then on day 10, there's a 10% permanent increase in demand. In this idealized system, she notices this immediately, sends an order to the factory, and the factory increases its deliveries. So let's take a look at a system with a number of delays. We have a perception delay, so before ordering, the manager averages sales over a 5-day period. We have a response delay. She makes up a certain percentage of the shortfall in each order, in this case 40%. And then we have a delivery delay where it takes 5 days for the factory to deliver the order. And as you can see, over time, the inventory starts to oscillate, and the oscillations start to grow larger over time as well. So this is not ideal. But don't panic, we can make changes to try to fix it. So let's look at the options, and as I go through this, please try to think of an option that you would prefer. So first, she could have faster perception. She could perceive the increase in sales faster. Secondly, she could have a faster response. That is, she could try to close the gap quicker. Or thirdly, she could have a slower response. And ultimately, there's nothing we can do about the delivery delay. So take a moment and think about the option you think would work best. So here's the first case. She's going to change how she perceives sales. So instead of averaging sales over the previous 5 days, now she's going to average them over 2. And as you can see, the graph is not very different. The inventory still oscillates out of control. In fact, in this case, the oscillations get slightly bigger. You can see that her desired inventory goes up faster. If we flick between the two graphs, you can see that the timescale just shifts slightly. There's not much difference. So let's try the opposite. Let's try slowing the response. And this is option 3. And in this case, she makes up less of the shortfall in each order. She orders 25% of the shortfall instead of 40%. And now the oscillations dampen. The peak inventory reduces to 2,380, and the wobble is smaller, and we start to converge closer on the ideal desired inventory. As we saw in this example, systems can react in counterintuitive ways. In this case, the store manager was reacting too quickly, not too slowly. We saw that some delays can have big effects, but changing some of the delays can have surprisingly small effects. Ultimately, real systems are more complex. They have multiple stocks and feedback loops and are inherently oscillatory, as we saw in this case. And human beings are not good at understanding nonlinear growths and interactions. As we'll see later, it's not always clear what the limiting factor of a system is. So how do we change systems? First, before making any change, it's important to observe the system, to get the beat of the system essentially. You could change an input or a variable like the contact frequency that we saw in the pandemic model earlier. You could also add buffers for the stocks, but if the buffers are too big, it can make the system inflexible or add cost or complexity. You could strengthen the balancing loops. That typically needs good information. You could reduce the gain of reinforcing loop. Doing this is typically more effective than changing a balancing loop. You could add new information, and that will enable new feedback loops, and this is something that we try to do in MongoDB. Ultimately, you want to build a self-organizing system, adding structures, loops, or rules. Now let's shift our focus to software systems. So let's take a look at the big picture. In this case, we're looking at a typical software system. So if we need to find the limiting factors or the bottlenecks in the system, they could be in a number of different places. First, you have your application code, whether it's the user interface code, which is interacting through an API with a number of application servers, or the software components that make up the application servers themselves. The bottleneck could also be in the framework that you're using. It could be Spring or Rails. There could be a bottleneck in the data driver, which is the MongoDB binding for a particular language or framework. And ultimately, there could be bottlenecks in the networks as well, either from your user interface code to your API or from your application servers to your database. So let's take a closer look at the MongoDB database service. Here we see the data driver, but now we're taking a closer look inside MongoDB Atlas. Ultimately, your application has decided a schema that could be inefficient, that could be the limiting factor or the bottleneck. You could have inefficient queries, and perhaps adding an index might help, although you could have counterintuitive situations. For example, if you had a collection scan where the working set doesn't fit in memory, these might be more efficient without an index. You could have a number of different shards in your applications. Here we see a shard with a replica set inside of it. You could have different types of cloud storage. Cloud storage is ultimately measured in disk I/O operations per second, or IOPS. A particular cloud provider might guarantee a certain number of IOPS for a certain type of drive. For example, it could be 240. And if you reach that threshold, any further accesses could be queued, resulting in a disk bottleneck. If you use a high-end PCI Express attached device like non-volatile memory, it could offer 1.5 million IOPS, and then a typical hard drive might only support 150. Let's look more closely at a MongoDB database server itself. On Atlas, it's not quite a black box, it's a dark gray box as we think of it. There are still a number of things that you can change. So for example, you can change the size of the CPU, the instance size, or the size of the memory. If we look at the MongoDB server for an on-premise or a private cloud deployment, really a light gray box, we can see that there are quite a few more factors that you need to take into account. The network bandwidth may become a factor or a limiting factor. The replication subsystem, you can configure that in different ways. Inside the database server itself, we use a storage engine called WireTiger. You can change settings for that. The server is built to use a number of libraries for the C++ programming language, like TCMalloc and Boost. You can change settings for those as well. You're running it on an operating system or kernel that you can configure yourself. You can change the scheduler, you can change settings in the operating system. You might be running the database on a virtual machine, and there you can select a different number of virtual CPUs or memory ballooning. You could have more control over the memory types. The WireTiger subsystem has a cache within it. There's the file system cache, swap, transparent huge pages, NUMA, lots of different things that you can change. On the CPU, you can add a number of cores. Again, you have more control over the instance sizes. And ultimately, on the storage side, you've got, again, a file system cache. You can change the read-aheads. You can change the types of disks and ultimately the controller caches as well. So here you can see a full list of the potential bottlenecks in this system. As you can see, using Atlas reduces the possibilities or the limiting factors that you need to consider. Ultimately, if you look more deeply at each of these components or elements of the system, they typically have a stock. They'll have a number of requests arriving. They might have a number of threads that are handling each of those requests, and then departures, which are completed requests on the way out. And some of these threads might actually interact by using the same shared resources. For example, a query being run by one thread in the database could consume WireTiger cache, slowing other threads. Some of the potential bottlenecks or elements are interdependent. For example, certain queries could use more memory, like wildcards or $near or sort or deduplication. Single-threaded workloads in your application code might be limited by I/O latency, either network or storage latency. Finally, you can use the Atlas Real-Time Performance panel to get a beat of the system, to observe how it's behaving. The panel displays operations that are running, connections, network traffic, the utilization of memory, CPU or disks, and even replication lag. To use the panel, the project owner must enable it first. So now I'm going to hand you over to my colleague Tom, who will talk you through two specific case stories and performance riddles.
Thanks, Jer. We have two cases here. The goal is to demonstrate a systems thinking approach to troubleshooting and performance training. Let's have a look at the first case here. This is a case that customer is running their MongoDB deployment on Atlas, which is a MongoDB database as a service cloud offering. MongoDB Atlas customer performing data load with Mongo import using an option, absurd fields. So what does absurd fields do? It modifies the import process. It will perform update on existing objects in the database if they match based on the specified fields, while inserting all other objects. Customer reports that the same workload was running a lot faster in October, which took 1 to 2 minutes, than in November, which took 5 to 10 times longer to complete. They are also seeing the disk I/O percentage utilization on data partition has gone above 90% alert frequently. Customers' workload is mostly periodic short bursts of updates. So here is the situation. Now, before we fully dive in for troubleshooting, let's ask a question to ourselves. Since there is a difference in behavior after a certain point, what has been changed? Now, let's have a look at the timeline. In October, customer was running their database on Atlas M40 instance type with standard I/O storage, which has a baseline performance of 240 I/O per second. Customer's database size was around 14 gig. Now, on October 30th, customer did a data load operation, which pushed the database size from 14 gig to 30 gig, more than double the size. On November the 1st, customer noticed the slower performance and started to get frequent I/O alerts. So since they were getting a performance hit and the I/O alert indicated a possible issue with the storage, customer made a change and upgraded the storage from standard to provision IOPS storage with a baseline performance of 1,320 IOPS before consulting with us. Customer saw no improvement after the change. In fact, the workload ran even slower. So they contacted MongoDB support. Now we understand what the changes are. We can dive in for the root cause analysis with 2 questions in mind. Why the workload is slower after the data size increase? And why the performance gets even worse after upgrading the storage? With those 2 questions in mind, let's get into the analysis. Now, this is the data size increase I mentioned earlier. We can see that the storage size was doubled from around 14 gig to around 30 gig on October 30th. This can result in increase in working set size. So what is working set? Working set is basically the amount of data and indexes that will be active and in use by your system. Let's compare the results between October and November. We can see that the workload took 1.5 minutes in October and took around 12 minutes to complete in November. The CPU I/O wait, which is the time CPU spent on waiting for I/O from the disk, peaked at 74%, which is already very high in October. But it is even worse in November, which peaked at 99%. This indicates the customer is having I/O bottleneck in both October and November. We see very high disk latency, both average and spikes in October, specifically the write latency, average at 27 milliseconds and peak at 280 milliseconds. It is much worse in November, which is 78 milliseconds average and 770 milliseconds peak. Now, please pay attention to the IOPS here. We see higher average and peak IOPS in October than in November. There's also an interesting I/O burst observed in October, but not in November. We can see that the number of I/O was beyond the configured baseline limit of 240 IOPS in October. Another thing to note here is the higher WireTiger cache pressure with more frequent aggressive cache eviction in November. Quick run through regarding how WireTiger cache works. MongoDB fetches data from disk if the required data is not currently in cache. the data is fetched from disk to the file system cache first, and then into the WireTiger cache. If the cache size is not big enough, we need to make rooms for the newly requested data. So the eviction process is here to help to evict the least recently used data out of the cache. This behavior indicates the cache pressure, which could be a result of the working set size increase. So what we have learned from the analysis: the disk was already the bottleneck in October. The data size change also increased the working set size, which made it no longer fit in memory. This has led to higher WireTiger cache pressure and more frequent need to fetch data from the disk. The result is increased demanding from the underlying disk. Now let's have a look at the differences between the two storage types. This customer is hosting their MongoDB Atlas cluster on AWS. The standard I/O storage from Atlas is using AWS GP2, the general purpose EBS volume. The provisioned IOPS is using AWS I/O1, the provisioned I/O EBS volume. They have different performance characteristics. There is a very important factor I would like to mention here. The GP2 volume has a burst bucket mechanism, which allows the EC2 instances to collect I/O credits while the system idles. And when workloads requires, it can burst the IOPS up to 3,000 per second for a short period of time, until the credits are all exhausted. However, this is not the case for I/O1 volume. For this case here, with the standard I/O configuration, the 240 IOPS, based on the pattern of the customer's workload, periodic short bursts of update, the IOPS could burst up to 3,000 per second until the credits are all exhausted. But with the upgraded provision IOPS, there's no burst possible. Remember the I/O burst we observed in October? The disk I/O jumped higher and the disk latency was lower in October. But in November, the peak IOPS was lower and the disk latency was much higher. Remember the two questions we have. Now we can answer those questions. The increased working set caused the slowness after the data size increase. And the customer's workload pattern works better with the general purpose volume. So what is the fix? Now, since we know what the root cause of the issue is, the fix is easy. Since the issue is started with the increased working set size, increase Atlas instance size, which will also increase the available memory to accommodate the larger working set in memory. In terms of the storage, you need to know your key performance target. Customers' initial setup of 240 IOPS, the standard storage, was already too low for their workload, since we already see disk bottleneck in October. But since customers' workload pattern is periodic short burst of updates, which makes accumulating burst credits possible, they were able to take some advantage from the burst bucket mechanism for the GP2 volume. If the customer is happy with the performance in October, they can go back to the standard storage and keep enjoying the benefit. But if they would like to further improve the performance, and if their workload pattern may change to something that's less periodic, more continuous workload, then it is best to upgrade with more IOPS configured. Now, let's look at another case. A customer running a local MongoDB deployment. Customer reports recurring episodes of replication lag. The replication lag could be from minutes to hours. So what is a replication lag? It is the delay between the time an operation occurs on the primary and the time that the same operation gets applied on the secondary for a given secondary node. The customer's workload is high volumes of updates to some extremely large documents. When I say extremely large documents, I mean the document size are reaching the limit of 16 meg. They are running MongoDB on huge servers. They have 192 cores of CPU, and they have 1.5 terabyte of memory. Their working set fits in memory. So what are some hypotheses? Since it is secondary replication lagging issue, could it be networking? Or could it just as simple as resource contention, even though they have huge server resources? Maybe not enough CPU, or not enough memory, or a disk bottleneck. Could it just be workload issue? Maybe the workload is too high. Or they have a bad schema design, inefficient query without proper supporting index, or some other components not highlighted here. Before diving into the troubleshooting, let's refresh our memory for what a system is. A system is a set of elements interconnected with each other. They function together, not individually. A single server is a system on its own, but the whole MongoDB replica set is also a system. Each node, either primary or secondary, works together and interactive with each other. We need to look at the whole picture and figure out what went wrong. So even though the reported issue is secondary replication lag, we need to look at the lagging period on both secondary and primary node. Let's first have an overview of the behaviors on both primary and secondary. On primary node, we noticed the replication lag on secondary node is aligned with the update workload on primary. So we can tell the lag is somewhat related to the workload. The MongoDB database write latency increases along the way. Note this is the database latency, not the disk latency. We then looked at the MongoDB logs from the primary, and we can see that their updates are using the write concern with W equals 1. Write concern is the level of acknowledgement requested from MongoDB database for write operations. The W equals 1 means the database will acknowledge the writes once they have been written only to the primary. We normally recommend our customer to use write concern majority, which the writes will need to be acknowledged by majority of the data-bearing members in the replica set, including the primary. This approach will throttle the writes throughput, as well as minimizing the chance of secondary lag. Now, on the secondary node, we can see low replication buffer and count. These are the size and the number of counts for data stored in the local replication buffer to be applied on the secondary node. Small values during periods of lag indicate a problem fetching data from the sync source, which is the primary in this case. It is, however, not having trouble applying the data on itself. In such case, you will see the buffer is full when secondary is struggling to apply data. Now we know the issue is most likely on the primary node. Let's have a deeper look at it, and let's try to figure out the possible areas of bottleneck. Since this is not a virtual machine, we can remove that from this list. For the analysis shows no issues with networking, we can rule that out. And CPU, the usage is very low, so ruling that out. The storage, there's no high disk latency, no high CPU I/O weight, so ruling that out. Memory usage is also looking good, and we did not notice any WebTiger cache pressure, so ruling them all out. There's no kernel issue in the system log, so taking that out. Checking the mongoD logs, and we can see that their queries are using proper index, so we can cross that out. Now, there are only 3 possible areas of bottleneck left: the libraries bottleneck, the schema and/or the queries are poorly designed. Now, let's look at some details of the memory allocator. For people who is not familiar with TCMalloc, it is Google's customized memory allocator that MongoDB uses. This is a memory management library that lies between the mongoD process and the operating system. We have noticed the replication lag on the secondary node started to build up when high number of TCMalloc spinlock total delay NS started to show up on the primary. This metric is the cumulative time spent by threads waiting on a TCMalloc spinlock to service a memory allocation or deallocation. High values indicate a memory allocator bottleneck. We also noticed that this workload has triggered an increased scavenge rate, possibly because it's allocating and freeing large buffers. That involves locking the page heap, so it can cause a bottleneck. The scavenge rate isn't all that high, but this is a huge machine, and there may be negative scaling effects, turning the scavenging into a bottleneck. Also to note that the high volumes of updates to large documents are possibly driving contention for an internal lock in the TCMalloc memory allocator. So now we know the possible bottleneck is with the memory allocator. What remediation we can do here? Internal testing has shown that TCMalloc lock contention is often aggravated, sometimes significantly, when threads contending for memory are executing on separate CPU sockets. We have noted that even the server has 192 cores, but the overall CPU utilization is very modest. Now, this is counterintuitive, but we can use NUMA-CTL to pin mongoD to a single CPU socket in this particular case. Since they are using a very small fraction of available CPU, having execution spread among multiple sockets is likely to be causing negative scaling effect. And the TCMalloc is one place where this can show up. We have reduced the number of CPUs being used, and this increases performance. Another thing that we can also do is to decrease the TCMalloc release rate. This will decrease the scavenge rate and could improve things if that is in fact the bottleneck. So the TCMalloc release rate, the default value is 1. This is to control the rate at which we release unused memory back to the system. Increase this flag to return memory faster, decrease it to return memory slower. In this particular case, we would like to decrease the rate to 0.5. We also mentioned earlier the workload is high volumes of updates to extremely large documents. We'll talk about this in more details later. But one remediation we could try is to improve the application schema design so this workload can be improved. Also, we mentioned earlier that we recommended customers to throttle their writes by using write constant majority. This is still a valid remediation. A bit of a warning. There's no one-size-fits-all here. Those metrics training may not fit for your circumstances. Sometimes you may see the same or similar symptoms, but the underlying issue can be completely different. You need to perform a thorough analysis and pinpoint the possible area of bottleneck before attacking the issue. Also, make sure to only make one change to one area at a time, so you know that which changes are making improvement. Now, the result. We worked with the customer and made the change to improve the memory allocator performance. After the change, spinlock is consistently lower, a couple of threads versus 50 to 100 before the change. There are still occasional spinlock spikes. Scavenge and decommit rate is lower. The operation rate, which is the reads and writes, are consistently higher, 2 to 3K per second. Before the change, operation rates started at that level, then tailed off as spinlock and lag build. lag is not building continuously now. There are, however, still occasional lag spikes. So now we know that the remediations we did for the memory allocator worked, but the replication lag is still not completely eliminated. What the remaining issues could be? It is possible that the remaining issue could still be negative scaling effects within a single socket. So maybe the server is too high-powered, and downscaling may help with this. Also, optimizing the workload and limiting concurrency at the application end could help. Now, let's have a look at the workload in details. The workload is high volumes of updates to some extremely large documents, approaching the 16 meg size limit. They are using the write concern WX1. They perform multiple updates to the same document and update the full document every time. The schema is also very complex. There are several layers of nested arrays. So how can we optimize? Using write concern majority to throttle the writes. Change update operations to modify only the fields that are changing, rather than overwriting the entire document every time. Avoid multiple updates to the same document, and avoid overwriting the same document multiple times. The last but not least, redesign the application schema to improve the efficiency of the workload. Now we have completed the two case studies. Jer will go through with you a checklist for solving performance riddles. Over to you, Jer.
Thank you, Tom. As we said at the start, we've been involved in solving many performance riddles. Here's a checklist to help you solve software performance riddles involving multiple components using an iterative problem-solving approach. First, you need to know your key performance target, so you know when you're done. Next, do some preparation and gather some data. For example, does your working set fit in memory? Then you can generate one or more hypotheses for the cause of the issue. If you have more than one, then you could prioritize them. For example, you could have two hypotheses, storage I/O or the queries being generated by the framework you're using. Decide which one to focus on first. Then you test and validate the top hypothesis to see if it's the limiting factor. Make one change at a time and observe the effect. If the change makes performance worse, try the opposite change. If you do improve performance but reach a new limit, you will need to loop back to look at the hypotheses again. The performance bottleneck will probably have moved. Finally, if you're a customer, contact MongoDB support. We have a worldwide team of more than 170 people, and we have solved many of these riddles in the past. Here are some resources you can use to learn more about performance tuning. Kevin's blog post helps you understand interactions between memory, disk, and read performance. When the working set doesn't fit in cache, disk performance does not generally affect application performance. When the working set exceeds available memory, disk performance can become the limiting factor for throughput, and we saw this in Tom's first case study. Our colleagues Matt and Henrik have written a 7-post series on the MongoDB engineering blog on performance best practices. They look at a number of different components and provide you with tips to identify the bottlenecks and fix them. I mentioned Donella Meadows' book Thinking in Systems earlier. It's a great overview. The Michael C. Jackson book goes into more detail on the different methodologies of systems thinking and applies them to management. It's available on the Safari Books online service if you have a subscription. The Brendan Gregg book looks at systems performance in general. A MongoDB database is typically part of a larger system, and this book will help you consider the whole picture. It's also available on Safari Books online. Finally, I'd also recommend a YouTube video by our late colleague William Zola. William boils all performance issues down to 3 principal reasons. It was recorded in 2014 when MongoDB was at version 2.4. The server was very different then with the different storage engine. Today on version 4.4, general purpose performance for all workloads is much better. However, William's talk is timeless and most of his recommendations are just as valuable today as they were 6 years ago. Finally, here's a quick recap of what we discussed. First, we talked about systems thinking in general and used examples from the real world. Then we looked at software systems and discussed many of the possible components and their potential limiting factors. Tom then walked through 2 case stories where he solved a number of performance riddles. Finally, we provided you with a checklist and resources so you can solve your own performance riddles. Thank you so much for spending your time watching this video. We hope you found this talk useful. We wish you the best of luck in tackling your own performance riddles. If you have any questions, please feel free to send us an email. You can see our email addresses here. Finally, you can also visit our virtual product booths to find out more about the new features in our products. We'd also ask you to share the keynote.